Okay, we can get started. So this is where we left kind of the last time, right? We have laid down all the foundational concepts, okay, for the simplex algorithms. Once those concepts are in place, simplex algorithm is nothing but this, you're just following this general idea we outlined very early on, right? First of all, we find a feasible solution now for simplex algorithm. Since we are dealing with specific linear programming problem, you are not just finding any feasible solution, you are actually finding an extreme point. Okay, to kickstart the algorithm. And step two, which is this step of verifying whether the given solution is optimal or not, right? We call this optimality prediction. So this magical step, you can only complete it if you are dealing with this convex programming problem. Okay, so that's basically, we talked about this general principle. Right? For convex programming problem, you can check whether a given solution is optimal or not without comparing with any other possible solution out there. Okay, you only need to compare with your neighbors. And linear programming is a special case of convex programming. Not only you just need to check the neighbors, you only need to check the neighbors who are also extreme points. Right? This is the concept of adjacent basic feasible solution we mentioned last time. And then that's it, right? If the given solution passes the optimality condition, the algorithm ends. Otherwise, you have found a solution that's in the neighborhood, which is better. Okay, so we just move to this new solution, and the whole algorithm starts a new iteration. Okay. Now. So this lecture, I'm basically going to, operationalize this idea to a specific example. So at least you can have some feeling of how the algorithms is working, what are the quantities that needs to be computed, and so on. I will just work out computation using this this example we started with in this for this lecture. Okay, and just copy down this problem here. So the problem we want to solve is maximize x1 plus x2 subject to x1 plus 2x2 less than equal to 3, 2x1 plus x2 less than equal to 3, then x1, x2 negative, right? Now, instead of using the graphical approach, right, which could be applied, we just pretend that we can't visualize this problem and apply this simplex algorithm, see how it works on this problem. The first step, as I mentioned before, the simplex algorithm, a lot of the design is actually based on this standard form problem. Okay, so we just first standardize the whole thing to a standard form. This one, subject to equals to 3, and then 2x1 plus x2 plus x4 equals to 3. And then we have x1, x2, x3, x4, no negative. Right? This is a standard form problem in a 4-dimensional space. Now, how does the first step of the algorithm should work? Right? We need to find an initial basic feasible solution, right? For this problem. Still remember what's the algorithms for finding this initial basic feasible solution? The standard form problem. If we have 2 constraints and 4 decision variables, right? Remember this the matrix is basically a kind of a fact matrix, right? The the algorithms for finding basic feasible solution is to kind of try to find a square matrix inside this fact matrix, so that the columns of this square matrix are all linearly independent. Okay. In particular, if we have just two equality constraints, we need to pick two columns that are linearly independent, right? Two columns that are linearly independent. And this is the example we worked out before, where you can have, these two columns, at least one pair of two columns easily found, right, which is column 3 and column 4 in this case. That's kind of given to you for free. Good. If I choose column 3 and column 4 as my basic columns, then x1 and x2 are the non-basic variables, which are set to 0. So you can, in this case, you can quickly compute what's the initial basic feasible solution. The initial basic feasible solution is, in this case, is 0, 0, 3, 3. Right, that kickstart the algorithms now. So we start from this point, and then we move to step 2, which is we ask ourselves, is this solution going to go? Okay, then we need to check the optimality condition. Now in this case, in order to verify this solution is optimal or not, then we have to find out the solutions that's in the neighborhood of this guy. In particular, we want to find out the so-called adjacent basic feasible solution. So let me just try to do the computation here. Here we don't have pictures, right? So we have to kind of calculate all these neighbors by ourselves. Okay. So we want to kind of compare this guy with the neighbors. Now, what do we know about the neighbors? Do we know about the neighbors of this basic feasible solution? If you just think about the definition of adjacent basic feasible solution, the definition says, I give you two extreme points for the standard form problem. They are neighbors if they share all but one of the non-basic variables. Now, in this particular case, right, the first extreme point has x1, x2 as the non-basic variables. Sharing all but one means you share just one. So the other extreme point, who are this guy's neighbors, has to share either x1 as the non-basic variable or x2 as the non-basic variable. Okay. So in this case, it actually has two neighbors. For example, we can pick anyone we want. Let's say we want to find out a neighbor who is sharing this x1 as the non-basic variable. Okay. So then we know that the x1 is already 0. This is the coordinate I do know for the first neighbor. The other coordinates, I don't know what they are right now. Yes, I don't know what the other coordinates are. Okay. But this is basically the neighbor I would like to find. Of course, you have another neighbor. This is the other neighbor, which is this is the second neighbor, which has the 0 for x2, that's the non-basic variable. The other 3 components you don't know. But one thing you do know is this one can no longer be 0, x2, for the first neighbor. x2 can no longer be 0, right? It has to be either x3 or x4 are 0, but you don't know yet, okay, which one it is. But what you do know is this guy cannot be 0. So essentially, you can imagine, right? If I start from this point, I'm going to move away from this point until I reach this point. When I'm moving away from this point, the first component has to stay at 0. The second component has to become positive. These two guys, I don't know how they will change, but eventually one of them will become 0. So that's basically the process of moving from this point to this point. Now let me just mathematically describe this kind of a process. Okay. So in general, whenever you have a point, you want to the process of moving from x to y, you can always express it as some kind of a you have some direction, say D, and then you can say specify your step size. For example, this is a unit step, and then this is 2D, this is 3D. Okay, by moving 3 units by moving along the direction for 3 steps, I reach to my destination line. Okay, you can set up an equation like this one, x plus theta 1. X plus theta d. Starting from x, I'm moving along along the direction of d for theta unit of steps. Okay, this direction of d basically captures the kind of a line. This x and y are sharing together, if you think about it. Since we are neighbors, I can always drive along the highway so that I reach to you, and this d basically specifies the coordinates of this highway. So that's the equation that I want to set up. Okay. So we are basically starting from 0, 0, 3, 3. And I'm going to move. Theta is my step size, which equals to 1 or 2 or 3, or it can be any positive numbers, indicating your step size. And the direction, okay. This is something that I need to specify. I know, first of all, the first component is 0. That's what I mentioned already. Because you always want to keep the first components to 0, right? My neighbor and me, we are both having x, y as 0. Now the second component, you know that it's going to be something positive. So you want to move away from 0. So you can basically assign any positive number here. It doesn't change whatever computations we are making. But whatever positive numbers you assign it, you can always normalize it to 1. Okay, 1 is something that's easy to deal with. Okay, you can normalize it to 1. Okay, and then the third direction I don't know, the fourth direction I don't know. So I'm going to kind of assign some unknown variables to it. Say D3, D4. All right, so this is basically how I describe. I move from this point along some direction. We have 2 components that I don't know yet, until the point when I reach to my neighbor 1. Now, how do I find out all these unknowns? We haven't utilized the constraint yet, right? So basically, I know that the neighbors and also the kind of the lines that connecting me and my neighbors, they have to satisfy all the constraints, because they have every point on this highway are feasible, okay, are part of this polyhedron. So they have to satisfy the equation. Now let me write down the equation here. So my constraint matrix is A 1, 2, 1, 0. And then I have 2, 1, 0, 1. Okay. So it doesn't matter which point on this line we are talking about. By the way, let me just write it clearly here. Theta has to be greater than equal to 0. Plus theta times 0, 1, d3, d4. Okay. This is some point on the line I'm moving. It doesn't matter which point I'm talking about. They have to satisfy the equality constraints. Right? That's just a requirement of repeatability. Then I just need to solve this equation. Yeah. Here I have 2 equations and 2 unknowns. We just need to do a bit of computation here. First of all, what's this matrix times this 0, 0, 3, 3 vector? You don't need to do the matrix multiplication with that. Sorry, 0. Why this is 0? This times this. Why this is 0? A times this one. 3, 3. Yeah, because this is what? This is our initial solution. So by feasibility, the initial solution has to satisfy the equation ax equals to b, right? So this is a, this is x, it has to equal to b, 3, 3. Okay, and then you are right? If this is 3, 3, this is 3, 3, subtracting it away, it becomes just this a times this vector equals to 0, 0. Are we okay? And theta, you can throw it away too. So eventually, it's just a times d equals to 3, 3. Sorry, 0, 0. Okay, so this equation I can simplify into. This is my matrix times my direction vector equals to 0, 0. Okay, let me just write out the equations more explicitly. So this is 2 plus d3 equals to 0. And then the second equation is 1 plus d4 equals to 0, right? Then I can solve the equation. d3 equals to -2, 4 equals to -1. Okay, now we found the directions that we are moving on, right? This highway. Of course, we haven't figured out is how far I can go along this highway until I reach my neighbor. Right? This is where you can utilize this non-activity constraints. Okay. Again, let me just set it up. So this is the equation for highway. Theta times 0, 1. Now I know that this is -2, -1. Okay. Because we have this non-activity constraint, everything on this line has to be greater than or equal to 0. Okay. Then if you just check, right, what this inequalities imply. The first inequality is automatically true, right? 0 greater than or equal to 0. The second inequality, 0 plus theta. Remember, theta is already a non-negative step size. Of course, it's going to be greater than 0. So I only need to look at the third and fourth inequality here. So this gives me 3 minus 2 theta greater than or equal to 0 and 3 minus theta greater than or equal to 0. Yes? Then what's the maximum step size I can take along this direction? Yeah, 1.5. So theta has to be less than or equal to 3 over 2. So this is as far as I can go. Okay. Now, if I just substitute this this maximum theta to this direction, then that's going to be 3 over 2, 0, 1, minus 2, minus 1 is equals to, we have 0, 3 over 2, this is 0, then we have 3 over 2. Are we okay? Now we exactly find the neighbor who is sharing the first x1 as the non-basic variable with the point I started with. This guy actually has x3 as the non-basic variable. Good. So this is basically how we compute this the neighbor for this guy. Now geometrically, it's also not that hard to visualize, right? In this even in this high dimensional space, I start from a point Now I found an edge that I can move. That's basically my computation for the d direction, right? I found an edge that I can move. When I'm moving along this direction to the maximum step, I hit a wall. Basically, I hit a constraint. The constraint I'm hitting is basically x3 greater than or equal to 0. Okay. So at the point when I hit this constraint, I'm adding one additional binding constraint. So this then determines another extreme point, right? So living on the edge, basically we are at the intersection of n-1 linearly independent constraint. By hitting another wall, basically we're adding an additional kind of a binding constraint. So in total, we again becomes a fixed point, this extreme point with n linearly independent binding constraint. So that's basically, visually what these steps are doing. Now, after all the computations, once I found my neighbor, what do I do next? And don't forget about the high-level picture, right? Don't be lost in all this algebra computation. What do we want to do in this step 2? We want to check 0033 is optimal or not. This is the kind of a step we are at. So we found the neighbor, then we have to compare. Is my neighbor better than my current solution? Okay. Now, of course, you know the objective value, right? The objective function. You can just substitute the two solutions to the objective function, then compare. But there's a quicker way of doing this. Okay, so you don't have to really substitute the two solutions. In fact, you can evaluate how does the cost change on this line when you are moving. Okay, because think about it. You give me any point on the line that I'm moving. This is basically the objective value of that point, right? C transpose whatever point that's on the line. I can compare this guy with my original solution. This is my original solution, right? I can look at the cost difference of the direction I'm going into and my original solution. The cost difference, you do the computation, then you found out that the C transpose X cancels out. It really doesn't matter what your current cost is. Okay, all I care is the following. All I care is about this quantity, C transpose D. So this tells me whether and how much I will increase or decrease my cost if I move along this direction by unit distance. Of course, if I move by theta units of distance, then that's the kind of total cost reduction or cost increase, depending on whether this is positive or negative. Good. So we can just compute this C transpose D. What's our C vector? Our C vector, if you just look at the objective, that's -1, -1, 0, 0. Okay, the slack variables have 0 coefficients. So in our example, C transpose D equals to -1, -1, 0, 0. And what's D? The direction we just computed is going to be 0, 1, -2, -1. Okay, if you do the vector multiplication, you end up with -1. So then this tells you what? By moving along these directions we just found, for a unit distance, you can reduce your cost by -1. Actually, you could reduce the cost by moving. Of course, if every unit of movement reduce the cost by 1, you want to move as far as possible. Right? Better move to infinity away. But you cannot do that, right? Once we already computed, the furthest you can move is just 1.5. This is the maximum step size, so where you will reach the neighbor. So that basically already tells you the comparison between you and your neighbors, right? the cost difference is going to be exactly 1.5. Your neighbor is going to reduce your cost by 1. So this guy actually, because of this importance in judging optimality, it actually has a special name, sometimes called reduced cost. So as long as reduced cost is negative, it means that you can reduce your cost by moving along a certain direction. Okay. Any questions about this? But that's step 2, where we are verifying whether the current solution 0033 is optimal or not. So by this, once you find out this is -1, then you already know that the 0033 is no longer optimal. Here. Now this is the point where different versions of the simplex algorithm can have slightly different steps. For example, in one version, or in what I'm going to adopt here, is basically once I find out this reduced cost is negative, then I will just move. I will forget about the other neighbors. Okay, remember, I do have another neighbor out there. I haven't kind of checked yet, right? But I don't care, because I already find out this neighbor has a lower cost than my current solution, then I just move to this one. Now, in some other simplex algorithms, for example, later I will briefly talk about this tabular method. That's in a lot of this textbook, they have these materials. In the tabular method, they will basically explore all the neighbors. And of course, in this example, it's very simple. I just have 2 neighbors, but when the dimension is high, you can have a lot of neighbors. In that case, they will try to kind of poke each of the neighbors and then try to compute the reduced cost for all of them. And then you can decide. It could be the case that multiple neighbors have reduced cost negative. So basically, I can reduce cost by moving here, or by go that way. Then you can have a choice. And I mean, there are a lot of heuristics arguments on which one to choose. For example, one method that some algorithms use is this kind of a greedy approach. Once you get the reduced cost for all the directions, you choose a direction where the reduced cost is the lowest. Right? But there's no guarantee that this gives you faster algorithms, because you're being greedy, right? This step you can reduce the cost the most, but it doesn't mean you can reach the solutions faster, because you have additional iterations that can go on. Okay. Maybe I go this direction, then I have to move additional 10 steps until I reach my optimal solution. It could be the case that by moving on the other direction, even though my cost reduced is just a little bit, but maybe the next iteration I just directly reach the optimal solution. So there's no guarantee. So I think for a lot of the large scale simplex algorithms, they will just do what I would do. Okay, basically, you don't compute the reduced cost for all the directions. You just compute one by one. Once you found out a reduced cost that's negative, you don't compute the rest. That saves you time. So that's some of the additional, more kind of a detailed implementation. Now here, as I said, I already found a neighbor that's better. I will just forget about the other neighbor. I'll just directly move to this new solution. This is the new BFS. That's the new BFS we just computed. That's going to be 0, 1.5, 0, 1.5. All right, then you just iterate. Okay, you can just repeat exactly the same steps. Let me just quickly do this demo here. It's the same thing, right? Now the solution I have has x1 and x3 as my non-basic variables. I want to find this guy's neighbor. It has to share one of the non-basic variables. It could share x1 or it could share x3. Right? If it is sharing x1, we're actually going back to this 0, 0, 3, 3 back. Okay, so that's why I'm just going to look at the neighbor who's sharing this x3 with me. Okay, this guy shared. This guy I want to move away from 0. Okay, so initially, this is what I know about my neighbors. I only know that x3 is going to be 0. Now let me just set up the direction that I can go to this guy. 3 over 2 and 0, 3 over 2 plus theta times. The first component I want to move away, so I will set a positive number here, which is 1. The second direction I don't know, d2, 0, and the last direction, d4. So that's the direction that I'm going to set up. Now we can speed up the computation here. How do I find d2, d4? It's basically a times d equals to 0. That's the equation I saw. A is 1210, 2101, 20d4 equals to 0, 0. Okay. Now this equation is 1 plus 2d2 equals to 0, and then 2 plus d2 plus d4 equals to 0. That's the equation. This can be solved easily. So d2 equals to minus half, and d4 equals to minus 3 over 2, right? That's the solution to the equation. All right. Now, what do we do next? Now here you can speed up again the computation a bit. You don't want to find out what the step size is first. Right? I mean, finding out the maximum step size, you can go to your neighbor, but the problem is, I can first calculate what can I reduce my cost or not, right? If it doesn't reduce my cost, forget about it. Okay, I don't even need to compute this guy. I can just move on to the next direction. So we can directly compute the reduced cost without thinking about the theta. So the reduced cost is -1, -1, 0, 0. And then we have 1 minus 0.5, 0, minus 3 over 2, right? That's the formula for reduced cost. And then that's going to be -1 plus 1/2, and all the rest are 0. So this is going to be -1. So this means that this reduced cost is negative. Okay, so that means this is a good direction to go. I found a direction that I can further reduce my cost. One step size reducing by 0.5. Then I want to find out what's the maximum step size then I can move. Then I need to look at this guy, right? This guy. So that's 0, 1.5, 0, 1.5 plus theta times my direction is 1 minus 1/2, 0 minus 3 over 2 has to be greater than equal to 0, 0, 0, 0. Right? That's the inequality constraint. From this, I know the first inequality is automatically true The second inequality, I have 3/2 minus theta greater than or equal to 0. And then third inequality is automatically true. And the last inequality, I have this one. Yeah. Then from this, I know theta is less than or equal to less than or equal to 1. This is the maximum I can go along this direction. And then we just find out what this new neighbor is. New neighbor is just 0, 3/2, 0, 3/2 plus 1 times unit step side 1/2 0 minus 3/2 equals to the first component is 1, second component is 1, third component is 0, the fourth component is 0. All right. Now you see this is indeed another neighbor, right? Indeed, we find out this guy which shares x3 as the non-basic variable, and x4 is the other non-basic variable for this guy. Oh, good. Now then you just iterate it again. You cannot stop here, okay? You have to do another round of iteration. Iteration 2. Right, your new BFS is now 1, 1, 0, 0. Okay. Then again, you try to move. Right, if you want to do the computation, I mean, you know what to do, right? Again, it has two neighbors. If I fix x3, then that's going to be where I come from, right? So you can just look for the neighbor which x4 is kind of fixed at 0, right? We want to move to this guy. This last one is the shared non-basic variable and so on. Okay, so I will not do the detailed computation here. I think if you understand the above steps, you can complete the last steps yourself. Okay, so once you did the computation here, then you will find out the reduced cost for this one. You compute the direction, you compute the reduced cost, it's going to be positive. Okay. So this basically means that you arrived at the optimal solution. Okay. That's optimality condition is not checked. The first neighbor, of course, is where you came from, so you already know. Okay, there you can if you go back, you increase your cost. Here, if you go to the other direction, you also increase your cost. That's it. You have checked all your neighbors. So the solution 1100 has to be the optimum. Right? So that's basically what's going on behind all the solvers. So they're just repeatedly doing all these number steps. Let me go back to the lecture notes. Where I have the picture drawn here as well. Okay. So just now, what I did is pure algebra, right? But every step you can visualize it on this picture. Right, we started basically for the standard form 0, 0, 3, 3 is nothing but in the two-dimensional space, it's just a projection of this guy. This 0, 0 guy. And then the first in the initial iteration, the kind of direction we found is basically this. Okay? We found the kind of the edge, the equation that representing this edge. And then we want to move along this direction. Right? Then the theta unit, the step size, you cannot let the step size to be too large, because once you take a too large theta, you will be overshooting. So overshooting means you will violate this constraints, right? X3 exactly is the slack variable, measuring the distance you are away from this constraint, right? If you're overshooting, that basically means your X3 becomes negative. Okay, X3 just hitting 0 means you just intersects with this line. That's where you will end up at this point 0, 1.5. So that's the first iteration we did. And then yeah, that's the reduced cost concept. You can just evaluate the rate of change in cost by moving along this direction without the kind of the visual assist of these contour maps. You don't need them. You just compute. You can compute what's the rate of change in cost. Yeah, that's the reduced cost concept I talked about. Now, once we reach to 0, 1.5, then our next step is just we do the computation. We find out, the equations representing this edge. Right, then I move along this edge again until I hit a wall where I finally end up at this point 1, 1, 0, 0. Okay, and then in the last step, that's 1, 1, 0, 0. And in the last step, then you have to check, by moving along these two directions to see what's the rate of cost reduction. And then if you do the math, you will find out the reduced cost along both directions are in fact 1/3, which is positive. So that's the certificate that you have that 1, 1, 0, 0 is indeed the solution. Okay. So the summary, if you fill out, all the steps we just did to the general algorithms I kind of outlined earlier, then that algorithm specialized to linear programming becomes this summary. Right? We are finding not just any feasible solution, but a basic feasible solution, and then the optimality condition is the same as checking the reduced cost for all the non-basic variables. Right, for every non-basic variable, I can fix it. Right, that's the non-basic variables that I want to share with my neighbors, and then I can check what's the cost. So there's the one direction that I don't want to kind of change my. Since we are sharing all but one, right? There's one of the non-basic variables that I want to move away from 0. So that's basically the direction represented by the reduced cost notation. Okay. For every direction that I want to move away, I can compute this so-called reduced cost. If all the reduced costs are non-negative, I'm done. The algorithm stops. Otherwise, I will proceed to this steps. Then you're just computing the step size that you should move along this direction. Okay. Again, as the first remark I mentioned earlier, for really large scale problem, you could have so many directions you could move to. It's just faster if you just once you found a direction that has negative reduced cost, you just pick it and directly go to steps. The second remark is, I think if you look at the textbook, the 3 books I gave you, I think all of them have this method, so-called tabular method. Okay, if you have learned this operations research course in your undergraduate, probably you have exercised on this tabular method a bit as well. So let me just briefly describe what this is about. Okay, I'm not going to cover it. So if you really look at what I did here, so I think my steps is purely focused on try to visualize the geometry behind. Okay, but this is not algebraically efficient, not very efficient, because I have to kind of first find out the equation and then solve for this D3, D4 for one of the direction. If this is positive, then I need to check my neighbors again, right? Then I have to repeat all these steps again within one iteration. Think about it. If I have a lot of reduced, a lot of non-basic directions, a lot of neighbors to explore, what I did here is basically inefficient for us to hand compute it. Okay. So the tabular method is basically a way to organize everything in an efficient manner. So basically, you do some. It's basically like doing matrix inversion, right? As long as you do these row operations, you can get this directions for all the neighbors. I can immediately get the directions by just doing this matrix, kind of like an inversion step. You can then obtain the directions to reach all your neighbors. And similarly, you can also directly get the reduced cost. Directly get the reduced cost for all the neighbors. Okay? Again, by doing this row operations on the matrix. Instead of, like what we did here, set up the directions, find out all the directions, and then do the kind of vector multiplication. You can, in fact, perform everything on the matrix itself. That's essentially what this tabular method is. But I think it's too focusing on the, algebra efficiency, and once it's very focused on algebra, I think a lot of geometric intuition is kind of is hidden. So that's why I didn't choose to talk about that. I mean, another reason is who solves linear programming by hand anyway. Okay? So there's no point of making hand computing faster, I think. It's also, by the way, it's also a torture. If to solve some of these linear programming problems by hand. In fact, I think I've been tortured twice myself. I learned operations research in my undergrad days. I think back then we have to exercise a lot of this linear programming problems of I don't know, the largest I solved by hand probably can go to seven dimension, maybe 8. I don't know. I don't remember exactly. 7 dimension, and then there would be say 5 constraints. 5 equivalent, 5 by 7 or 5 by 8 kind of a matrix. And then I suffered that again when I went to grad schools. Okay, I learned linear programming, and then we have to do a lot of homework problems and stuff. So that's focusing on that. For those dimensional problems, of course, you cannot follow the steps I'm doing here. That's a lot of work. Okay, I have to compute pages of pages. But if you do this tabular method, you can do it faster. But I mean, it's still a torture because if you think about it, some of the problems, I think some of the textbook I gave you, it has some exercises like this. Okay, please ignore them. Because the numbers there are not as nice as this one, right? Think about it. I give you a kind of A matrix that has some weird numbers, say, 19/17. And then you have to do this solving the equations by hand with all these real numbers. That's a torture. And the second torture is, think about it. What happens if you make a small mistake in the first iteration? All the following steps, even if they are correct, they are wrong. Okay, the final answer is still going to be wrong. Okay, because a tiny mistake, right, in the first iteration will affect everything that's down below. So there's no point of doing it. So don't worry, and you can ignore all the exercises that related to tabular method in all the books. I think the important thing here is just to have a high level geometric picture, right? You can try to whenever you think about the simplex algorithm, whenever you utilize the solvers, as long as you can visualize, the algorithm is performing, you have a polyhedron, the algorithm is basically starting from some of the corner point of the polyhedron, and then moving along the edges to the next one, and then to the next one, and then to the next one. Eventually, we'll find out the optimal solution. I think that's pretty. What I do want to emphasize for this part of the lecture is basically how do you think about this extreme point in a high dimensional space. When you don't have the picture, you have to rely on algebraic equations. So that's where I think you should probably know how to characterize this so-called extreme point by purely through algebraic equations. Are we good? Any other questions about this part of the lecture? Yeah, good. So that finishes up the simplex algorithm. I think that's one of the fundamental concepts in linear programming. Now let me move on to the second, I think, again, a kind of a big theoretical part of linear programming. I mean, not just linear programming. In fact, this is actually a theory that's behind all the optimization problems, the so-called duality theory. It basically gives you a new way of looking and thinking about this optimization problems. So as I said, it's going to be a theory about general optimization problems, not just linear programming. I'm just going to motivate using a nonlinear problem. Okay, later on, then I'm going to specialize all the discussions to linear programming problems. Let's try to look at this this quadratic. This is a quadratic programming problem. Right. So what we want to do here is to think about this problem of z equals to minimize x squared plus 1 squared, objective subject to x plus y equals to 1. Okay. That's our optimization problem. Now, first, any idea? We're solving this problem. This shouldn't be a too difficult problem, right? How do we solve it? 0.5. Oh, you are quick, but I'm talking about the method.
Oh, the method.
Yes.
Actually, I thought of it because I want it to be squared, so a decimals, a number less than 0 squared will be smaller than 1. So I want both numbers to be smaller than 1 equally. But I think that's not a...
Yeah, that's a heuristic thinking, I think. Yeah. Your answer is correct.
But it's not a way a machine would think. So
yeah. Any systematic idea in thinking about the problem? Right, your idea, I think, won't work if I change the coefficient here. Right? For example, it's still x plus 3y. Well, what's going to happen?
Oh, let's substitute, right? Substitute.
Okay, very good. Substitute, very good. This is one idea. Yeah, I'm not asking you to solve the problem. I'm just providing me an idea in how to solve it. Substitute. Because x plus y equals to 1, I can actually eliminate one of the decision variable from the problem, right? So the problem is actually equivalent to minimize x squared plus 1 minus x. Yes. So this becomes a one-dimensional optimization problem now. What's next? I substitute it. What's the next step? Solve this how? Okay, take the derivative, right? You take the derivative and then you set the derivative to be 0. Yeah. That's the derivative. Right. 2x minus 2. It's 2 times 1 minus x equals to 0. This gives you x star exactly equals to 0.5. Good. That's okay. Any different method? This is 2-dimensional. What can always work for 2-dimensional problem? Yes, right. We can always do the contour approach. We can visualize, right? As long as it's 2-dimensional, it's good. Okay. We can visualize the stuff. This is x, this is y, x plus y equals to 1. That's basically this equation. And then we have the contour, right? In this case, the contour is, again, circle. We talked about it, right? This is basically the L2 kind of a distance. Contour like this. Okay, circle. I mean, these contours are not feasible, right? These are too small. It doesn't intersect with the line. I want the smallest one that still intersects the line, then that's basically the tangent. And this is the optimum solution. Again, you can find out this is going to be 0.5 and 0.5. All right, these are all good. Now let me try to ask you this question. So we already see the linear regression one, right? That's a quadratic optimization problem as well, right? If we think about the sum of squares. Back then, when we solved that problem, I said you just directly take the derivative and set the derivative to be 0. And similarly here, right? We did the derivative, set the derivative to be 0 here. Why can't I just do this with my original objective here? I mean, it's 2-dimensional, yes. But for 2-dimensional problem, you can actually, again, take the partial derivative. It doesn't matter. I can take the partial derivative of the objective function, this x squared, plus y squared with respect to x first, and then take the partial derivative with respect to y first. Maybe then I can set that to 0. Why I can't do that here? Simple constraint. Very good. If you set this to be 0, what do you get? 0, 0. Right? This 2x equals to 0, 2y equals to 0. You get 0, 0. It doesn't satisfy the constraints. So that's why you can't directly do the derivative, okay, to the objective. So this is the very important point from, say, some of the optimization problems you probably have learned in the calculus course. Usually in the calculus course, when you learn about the derivative, how it can help you to find the maximum and the minimum, there they don't talk about constraint at all. Right? Just give you a function, and then you take the derivative, you compare some of the stationary point, and then you find the max. But for all the kind of linear programming course part, we never use the derivative at all, right? Why? Exactly because of the constraint. All the difficulty actually lies in the constraints, not in the objective. And for linear programming problem, if you don't have constraint, what do you get? Linear programming problem. If I don't have any constraint. Yes. Right? It's just a linear function, right? You always kind of blow up to negative infinity or positive infinity if you don't have any constraint. The problem is kind of trivial. So all the interesting stuff lies in the constraint, right? We are analyzing, we spend 2 weeks analyzing the polyhedron, the extreme points, how do you move along one point to another point. All the works are there. Okay. For nonlinear programming problem, it's kind of similar. Okay. Once you have the constraint, the next thing is kicking. Okay. Some of the standard algorithms don't work anymore. Of course, for nonlinear programming problem, even without constraint, the problem is not that trivial neither. Okay, you still have to kind of do the derivative and analyze the derivative stuff. So, so that's one remark about this constraint problem. Now, this brings me to the third idea that I want to talk about, which is going to be kind of leading us to this duality theorem. So for some of this optimization problem, if the constraint is the one that's very difficult to handle, let's think about the following idea. Why don't we just throw it away? Let's try to solve this problem. That's it, without any constraint. For this one, we exactly talked about it, right? For this one, you can then do the positive derivative, set the derivative to 0, right? In fact, you don't have to do that. Visually, you already know what's the optimal solution here, right? Xy equals to 0, 0. Optimal value. 0. Yes. Right? We can quickly solve this problem if there's no constraint. Now, of course, you may ask, so this is not the original problem I want to solve, right? You're solving a different problem. What's the point of this? But this is the question that I want you guys to think about. So this problem, yes, without the constraint is easy to solve when we have quickly solved it. But do we learn anything new here? Okay, that's the point. Is our effort in solving this problem completely wasted, or I get something out of it, at least? So that's the question I want you to think. If yes, what do we learn from solving this? What do we learn from solving this problem where I just throw away? Let me try to kind of refine the question a bit. Okay? More specifically, I wanted to kind of think about the following question. What do we know about this value? This z. Right? The z value is basically the optimal value of the original problem here, right? So this one, without solving it, I don't know about what z is. Okay. Now I don't know how to solve this problem. What we did just now is throw away the constraint and solve this problem. Okay. I know that the problem below has an optimal value of 0. Do I learn anything about z? Yes? Z is bigger than 0. Are we okay? So this is what we call zero is a lower bound to z. Are we all good about the logic behind? And this should be intuitive, right? Because in the original problem, you're kind of hard constrained. Your hands are tied. Whenever you choose x, y, it has to satisfy x plus y equals to. Now in the problem below, there's no such constraint. You can do whatever you want. Then of course, you will never do worse, right? You will never do worse. So that's why 0 has to be a lower bound to the original problem. Okay, you will never do worse. Well, in other words, the original problem, the optimal value of the original problem z has to be greater than equal to 0. So not completely wasted by looking at the problem here. I know at least something about this unknown value of z. So that's the important idea that I want to kind of generalize. Are we all good with this one? 0 is a lower bound.
Then would you recommend taking that step of removing the constraint and trying to find the other side of the bound?
So can you repeat that? What do I recommend here?
I'm just wondering if we should always try this step 3 of removing the constraint to find the other side of the bound.
Yeah.
Is it something that we should always try when you're
I will get to that in a minute. Not only you should try this, you can try something smarter than that, in fact. Okay. So this is just the first step of the idea. Okay. I mean, I'm just first setting up to let you to kind of understand this intuition. Now I will try to generalize this. So the method I'm moving to is called the Lagrangian relaxation. you probably already see, right? Just throwing away the constraint completely is kind of stupid. I want to take this constraint into account. Okay, but the problem is the above hard constraint one, I don't know how to solve it. Okay. So the generalization of this throwing away the constraint is basically making the constraint soft. Okay, instead of just throwing it away, I make it a soft constraint in the sense that I allow you to violate it. It doesn't have to be strictly satisfied. I allow you to violate it, but whenever you violate it, I charge you some penalty. Okay, that's basically the so-called Lagrangian relaxation. So this is where I'm going to head to. So in other words, we are trying to solve the problem of the following form. So let me try to explain a bit here. So the P is basically the penalty I just mentioned. This is sometimes also known as the Lagrangian multiplier. So when I'm setting up the problem, you have to tell me a penalty first. You can pick any favorite number, doesn't matter. You pick a number, then I can set up this soft constraint problem. Yes? And this 1 minus x minus y is basically a measurement of the degree of violation of the constraint. Yes? If it is 0, then you're perfectly respecting the constraint. Constraint satisfied. If it is positive, you are basically violating the constraint in one way. Right? We are saying that x plus y equals to 1, right? If it is positive, your x, y are too small in some sense. Right? If it is negative, then your x, y are too big. Okay? So there are two directions of violations. But we need to be careful when I say this is a so-called Lagrangian penalty, because this is a linear penalty. Okay? By just using a linear penalty, you can only penalize one direction of constraint violations. And for example, if P is positive, then when you are choosing x, y to be too small, I will charge you money. Okay, you have higher cost. But of course, you can then say I choose x, y to be very large. Then I'm forced to reward you the money actually for those kind of constraint violation. Okay. The reverse can happen if I choose a P, the penalty will be negative. Are we okay? Yeah, so different penalty will have different effects. So that's the point here. Okay. And the whole function here also has a name. And notation wise, it's sometimes denoted as LXYP. So this is called Lagrangian. So that's the soft constraint problem. Now, let me give this optimal value to this soft constraint problem. Again, a notation. You first pick your favorite number P here. Then I'm going to solve this soft constraint problem. Then I get an optimal value, right? You pick another P, I solve this problem, I get another optimal value. So this defines a function. Okay. That function I'm calling it to be GP. Now the question here is, again, what do we learn from this exercise? From solving this soft constraint. One example, the naive idea we had earlier by just throwing away the constraint is a special case of the idea. If you just throw away the constraint, that's equivalent as choosing the P to be 0. Right? Then you're just throwing it. And in that case, I already know the value here, right, of G0. G0 is just 0. So this is basically what we did just now. Directly storing away. Now you can see this, the idea is kind of a slightly smarter, right? Instead of just using a 0 penalty, I can choose something else, okay? Maybe I can get a better idea of what Z value is. Are we all good? Now, here comes the most important claim here. I'm going to claim here that no matter what penalty you choose, name your favorite number, P, I always have the optimal value of this soft constraint problem is always going to be a lower bound of my hard constraint problem. In other words, the GP is always less than or equal to Z value, no matter what P you choose. The previous one is again a special case. If you set 0 here, then we already kind of said that Z has to be greater than or equal to 0. Now I'm basically saying that this is true, universal. Are we okay? Now, let's think about why. Okay. This is the argument that's so commonly used in optimization, okay, in comparing different optimization problems. So the argument is the following. So think about, say, you guys are solving the hard constraint problem. So you do your best, right? You find out using the best algorithm out there, then you can find out the optimal value of Z. Okay. Now I'm responsible for solving the soft constraint problem. Okay. I don't have to respect the constraint. X plus y equals to 1. I don't care. But the problem for me is that I will have some guy telling me, charging me money. Okay, this is P. Think about it as some kind of a government out there who is going to impose a penalty if I violate the constraints. My claim here is basically it doesn't matter how much money the government is charging me. I can always do better than you guys. Always have lower cost. I mean, not strictly better. I could do the same, but maybe I could do better. But I will never do worse. Are we okay? So that's basically what the claim here means. But why? Here's the argument. So I can first, so you guys are solving your problem, right? You do your best, you find some x, y. What I will do is I will copy your solution. If I just copy your solution, what's my cost? 0? My cost is 0. E. I copy your solution. What's my cost? Or how does my cost compare to yours? Same. Yes? Because if I'm copying, you guys are solving the problem, you have to respect the constraint, right? Your solution has to be x plus y equals to 1. I'm just copying yours. So whatever penalty is going to be, it doesn't affect me. Yes? And I'm achieving exactly the same cost as you guys. Doesn't matter which solution you get. Even if you do your truly best, cutting edge algorithm, find the optimal solution, I can still copy it. I can achieve exactly the same value. So my argument is that I will never do worse than you guys. Is that okay? I could do better. Why? Maybe if the government doesn't charge the price right, maybe I can find a loophole. If I can deviate, doesn't respect the constraint in some way, maybe I can even further reduce my cost. I can do that, you can't, because you're hard constrained. No matter what you do, you have to respect this x plus y equals 1. I don't have to, but I always have the choice of respecting the constraints. Okay. Are we all good? So this is very important. Okay, I want this the logic behind this argument to be crystal clear. This is a very commonly used argument in comparing the optimal value of different optimization problems. Okay, it's just a kind of a copycat kind of argument. So that's why, a lot of, I mean, from my previous kind of experience with the student, you may find this surprising in the sense that, when P is very large, it seems like that objective function here becomes super large. Seems that I'm doing very worse because there's a government who can charge me $1 million. Okay, that sounds scary, right? But I have the freedom to choose X, Y. Remember, always remember that. I have the freedom to choose X, Y, even though you are imposing, say, $1 million penalty. If I just respect the rule, I'm fine. Okay, but maybe this $1 million penalty has some loophole in it. Okay, maybe I can figure out an X, Y that can, I mean, in this case, you can actually do that. In fact, if it is $1 million, P equals to 1 million, what do I want to do? If I make my XY too small, I will be penalized super heavily, right? But I will make my XY super large. So I change this $1 million penalty to $1 million reward. Okay. So in this case, I can decrease the cost super fast. So that's basically why it doesn't matter what P value is, you always have a lower boundary value. But another analogy you can think about is, right? Think about the homework problems, right? Suppose you let your friend copy your solution. What's going to be the grade of your friend and you? Could be the same, or your friend could do better. Right? Your friend could say, let me think about this guy's solution. Right? Maybe he or she can find a mistake and then correct it. Okay? He or she can do better, right? So exactly the same argument behind why this is this copycat. Are we okay? What does this tell you about the homework? Do it alone, okay? You could discuss with the friends, but don't just do the copy. Okay? You won't have some of your own thinking. All good?
I have a question.
Yes, please.
So, I understand what you're mentioning, throughout the process, but I'm just wondering that the penalty of 1 minus x minus y is because of that you have the constraint of x plus y equals
to 1, yes.
Yeah, so if there's a case that today we have another constraint which is not this kind, like x plus y equals 1, does it mean that we also need to change it to that thing?
Yes. It doesn't matter what constraint you have, you can always apply the same idea.
And the result would always be the same, that G of P would always look
Yes.
less than C.
Yes. It doesn't matter. It doesn't matter what constraint you have. As long as I'm relaxing it, I can always do better. Okay, this is the idea of Lagrangian relaxation. Since I'm changing hard constraint to soft constraint problem, I can always do better.
Yeah.
Okay. Now later on, of course, we are going to kind of repeat the same steps for linear programming, which becomes much more complicated. There will be a lot of more constraints, but exactly the same idea goes. Any other questions? Good. Now, once I understand this, okay, now I can try to solve the soft constraint problem because that's the promise I gave in the beginning. Without any constraint, the problem should be easy to solve. Okay, we should be able to solve this soft constraint problem. Yes. Indeed, right? Once I don't have any constraint, we can just do this partial derivative stuff. Yes. So for the soft constraint problem, then I can do Lxy. So they do have some p here, but it's just a constant for now. Okay. I can check the partial derivative of this guy. That's going to be qx minus p. I set it to be 0. Okay. And let's look at partial derivative with respect to y. That's going to be qy minus p, again equal to 0. Good. So from this, I can then solve x star equals to y star equals to 2 over 2. once I get the solution, this is easy, right? This is indeed as promised. This is easy problem. Once I solve this, then I can go back to my optimal value function. I can find out what GP is. For every value of P, I can write out the function for. So GP is then equal to x squared, this is x squared, plus y squared, this is y squared, then plus P times 1 minus x minus y. Yeah. This equals to, this is P squared over 2 plus P times 1 minus P. So this is going to be P minus P squared over 2. Okay, so in fact, it doesn't matter what P you give me, I can easily find out the optimal value of this relaxed problem. And using this, I can even draw a picture. You can visualize what this function looks like. It passes through the origin. It has another root, which is 2, right? It crosses 2 at 0, 2. And this function looks something like this. Right? This is GP, the quadratic function. Now, directly throwing away the constraint correspond to this one. Okay, now let's get back to our original question. Why do we want to throw away the constraint in the first place? First of all, we don't know how to solve the hot constraint. We not only know how to solve this unconstrained problem, that's first of all. But again, I mentioned, solving the soft constraint problem is not useless. You get something out of it, right? Because for every P you solve, I know a bit of information about the Z value, because that's a lower bound of Z. If I want to get the most information about Z, which penalty should I choose? If I want to get as much information about the Z value, which penalty should I choose?
Well,
Yes.
setting it at 0 to find lower bound.
Setting P equals to 0, that's one lower bound. Yes, I know that's lower bound is 0. So then I know that Z has to be greater than or equal to 0. Okay, but for example, if I set P to be 1,000,000, according to this picture, in fact, we can compute that lower bound as well. That's a lower bound too, right? If I set P to be 1,000,000, it's going to be something like negative 500,000. So then you know that is greater than or equal to negative 500,000. But is that useful? I already know Z greater than or equal to 0. I don't need to tell me that it's also greater than or equal to minus 500,000.
Most optimal.
The most optimal, most specifically,
Here,
in the picture, the maximum. Yes, I want to choose the P that maximizes this function. That's basically gives me the best possible lower bound, which gives me most information about the Z value. Okay. Once I know that, everything else doesn't matter. It becomes redundant information. Are we good? So this brings us to a new optimization problem, right? I have a new optimization problem, which is maximize P. I want to find out what is the right penalty so that I can have the best possible lower bound to my original value. So this problem is called the do problem. And correspondingly, of course, the original problem that we want to solve, this problem we started with, this hard constraint problem, is called the primal problem. Are we okay? The duality theory is basically trying to think about the relationship between these two problems. You have a primal problem by doing Lagrangian relaxation. For any penalty, I can find a lower bound. Then this brings me to this dual problem of finding the best possible penalty. Okay, what's the right penalty I should give to the constraints? Now, for this example, at least, the dual problem is kind of easy to solve also. We don't have any constraints. Right? We can just, again, do the derivative, which is 1 minus p equals to 0. Then I know p star equals to 1. That's basically this point. Right? Basically this point on the picture. And then we have, let me call, by the way, let me call this optimal value for the dual problem. Say, let me call this W. Okay. Then I know that W equals to 1/2. Are we okay? So this is the value for W. Let me use a different color. Use the red color to denote whatever that's related to the dual problem. Right, because this is the best we did, right? This is the best we did. So I know that not only I know that Z value is greater than or equal to 0, I also know that Z is greater than or equal to 1. That's the best information we can get from this exercise. So Z value has to be somewhere. I don't know where it is, but somewhere. Are we okay? Oh, good.
Sorry,
Yeah.
I have a question.
Yeah.
Okay, so after actually it's before this. So after you do the partial derivative
Yeah.
of the
Lagrangian. Yeah.
Lagrangian, then how do you why do you sub the solution back into GP?
I'm not substituting back into GP. I'm substituting into the Lagrangian, into the objective function. So for a given p, right, I get a solution x star and y star.
Yes.
And then I substitute this x star, y star into the objective function, and I get the optimal value. So GP is the optimal value, okay? It's the optimal value. It's not the objective function.
I get it.
Yeah.
So you solve this sort of like solve using partial derivative the optimal, then you sub back to the objective in order
Yes.
to okay, yes.
So I'm basically evaluating what's my optimal cost. I'm just evaluating what's my optimal cost as a function of p.
Okay, thank you.
Any other question? But the picture here is okay, right? So we know that z has to be above the whole curve, above the whole GP. Now, let me ask you this. What's the value of z? It's not that hard to solve anyway, right? We're just pretending we don't know how to solve it for now, okay? What's the value of z? We have some method just now, right? In solving this, what's the value of z? Also 1. So what I draw here is in fact not accurate. What the actual position of z is over here. This is also z. Somehow, magically, they coincide. Okay? this W exactly equals to the Z value. So this is not a coincidence. This is, I think, one of the most beautiful results behind the duality theory, which is called strong duality result. This is not true for any optimization problem. Okay? It's only true for a class of, we talked about the easier class of convex programming problem. A large class of convex programming problem, this is absolutely true. This is not a magic. Okay? As long as I approach the problem from the dual, I get exactly the same optimal value as the prime. Non-convex problem, you don't have this. But of course, this is I mean, you only need to know this result. I mean, within the scope of this course, I probably cannot tell you why, because it's a quite big result. What's easy to understand is the kind of the weaker part called the weak duality result. The weak duality result is basically saying this W has to be less than or equal to Z. So that one we already talked about. Right? This is easy to understand. You provide a lower value. But why does W exactly coincides with Z? That has to do with the geometry of this optimization problem, with geometry of convex set. So let me just stop here first, and then I think after the break, we wrap up, okay? We wrap up everything we learned from this exercise. And then we move to the specialized idea to linear programming.
Dave, I saw the that's been so popular. We haven't split and something.
Randomize already.
6 minutes.
Yes.
It's not only back to the actually it's I don't have there's a story even though I thought I got it I still don't have it. Okay, you okay it's the first one. This problem such a if I mean next year that's not as the arrow whatever.
He says the optimal value.
GP is the objective, right?
No, I think this is optimal value.
GP is the
optimal value, not the objective. Minimize x squared.
or is it all this? Okay, so you know some back is good. Okay, something that is the minimize x squared plus. Oh, basically this one.
So many different problems that could be
You ask them
From the like that. Yeah.
One is the Lagrangian, one is, I think, quite. I think.
You should be understand 80%. We should see how sexual people watching the recording. We should go you mention.
I'm afraid I think.
But it's something very hard to ChatGPT about questions. Don't have them all. Yeah, if I do it alone, without ChatGPT, I will go.
Try using. Yes.
But he comes to this VS Code.
That's how I'm using this.
Not direct, not direct.
Using vision. You need to plan the folder. I just pick in all the things.
Direct.
Yeah, the same.
That's what it is. Actually, the only problem is just.
You put SGP. You make a P or something.
Yeah, if without, if you don't follow, you won't even,
Yeah. I thought just please.
if you don't have this.
I
then
did
you'll block.
not.
Yeah, that's why,
I didn't
that's
know
why
that
it's
actually.
it's being used in the curriculum.
确实还是Google 出来的。会那个I use ChatGPT，所以问我印度的说的嘛，因为这 system 的最大是
But that has to optimize it.
because I download the Apple notebook 嘛。The license you just copy and paste on Google Colab 嘛。
Yeah.
Obviously, please, I just
need the key。
I don't even need to download Google, I just need the license.
对，actually it seems to be the case 啊，it seems to be the case 啊。
I hate Google because they always charge me the.
They use what you want, they use。
你要不再讲一个？你听过吗？我听是听过，因为我玩手机。
I thought they give a lot of space. You know, you must be using a lot of. I already use it, so.
But they did give free.
明天我学习有求。
You also didn't use that. So what's what like you do that?
Learn how to.
Yeah.
We don't have some like ML model. All those people.
It's just a tab.
哥们儿，
Yeah. We have the confidence model, so yeah, how they do it. Only the.
我今天上课课。
Just SQ.
SQL is really good. Train with SQL. I want you to high tracker of attention to it. I want to train like yeah. I want to train about. I think probably those once we learn that music.
Concentration.
Well, what of it could help is this make translation. Yeah. You should have a HR profile in that trade management.
Right. If they say you have a last very brief.
That's fast.
The new book. Yeah. Can take some more money.
I graduated this sem, so I won't be a student at next country. Okay, Pauline can join me.
Many things to do.
You're asking me.
But I think the ultimate takeaway is that you try it in the market, most likely on the team. Like you should your product and try.
Oh yeah, still those numbers. How
Then
we
you load up your CGI.
haven't done. I wanted to for myself. outside. I try to do some.
But the KPMG nature. Now go back. It's still.
No, those big bombs, yeah. And then I really sleep very late. Yeah, so for to see. It's that maybe just put the project on the link, say that I did this and show the video or something.
Wonder how you do that with them.
Oh, no. But now after I went to the therapist house, I realized that we really how to run our own. We have no, I have no key now. But yeah, so
It's me.
I want to is a multiple employees by the thing the thing and it's so you know our basically our product like each person each employee was we have any question by them
We sort of assume there's going to be use within the commercial.
people will not confuse it. Maybe that's something that we'll get.
Because in the
Because we don't have the before
yeah, they asked the critical question, have you tried your system in the HR? They did ask some of them.
You just.
Oh, I think it's just the product stuff. Sorry, not some, but not as good as. But yeah. Yeah, you're
The
right.
quality
Yeah.
of
But they're good package and they're damn nice.
that's it. Find it out.
They hope the you also someone who just like I give him credit for that. But seriously, sometimes it's just too stubborn. We almost didn't manage to start with the slide. What? It's terrible. We were still arguing at like 11 o'clock midnight. Now sometimes we follow our if not then the things that we're doing for the last 1 month is all going to go down the drain. I was like so damn pissed.
A lot of reasons. This is the kind of submit 1 week in advance. The one our PT 5153. I really wanted to do more things, and then just like, no, I'm gonna submit.
I just want to get rid of the thing. I'm a student of the first week of the June 40, I'll finish all my work. I cannot keep it until then.
So
One thing about it, if you think about it,
then
you
you can
change,
play.
or will they improve along the way?
He didn't change.
I will want it, I will like, I can't do it.
He did for a week before.
I was like, forget it lah. Submit me, submit already. I mean, how much? Even if I get that one, how is it? How is it going to be?
Minus 100.
Okay, if let's say I fail the test, then maybe you will do something about it.
But still not bad. It's
But after my undergrad, like, you know, I might just pass through. But no, not. Still a B. B doesn't cover.
That was sick. It was just everything.
After a while, it just really became like.
I cannot say I over kind of also ask me more.
Unless the person can put it with your unreasonable, but I don't change our diet horrible. That means the first step is wrong, then all the way wrong. Then okay, that one I will change. Forget it, just do it.
But you also mean the 51 10 the yeah okay.
Not yet.
Not yet definitely.
So do everything really just start with everything.
It's just minor editing, right?
So you like which tool to draw?
I
So
CVS UI.
It's
It's sure very difficult.
without everything. Before you even started the whole thing, the whole thing is
actually the draw IO can draw like figure, right?
finish everything in the first.
You're
Simon
okay,
Mayer is the-
you're okay, like no dispute.
As in, okay, we run through the whole thing together with him, then discuss, okay, just can
But are we still changing anything?
Do you want to do partial key?
We never.
It's
I was thinking,
more alive
Say
with
now.
P1, the P1.
Actually, I was thinking,
so it's
The P1 doesn't have aggregation one. I'm not saying that
but we don't have our results is not result, our results is a relation, so.
Yeah.
So we cannot have I mean, for our group, so we cannot.
change the
If I have a partial key, the bit in result is different from the level, right? But we, our result is a relation, so it cannot be a partial key, right? It's just
It's a-
just a,
They have attribute.
just an attribute of it.
Partial.
Yeah. Should be like, let's say your partial key is like your stage or your exit, right? You will need to push the number in order to find out, in order to collect your whatever.
Let me
There
talk about
became a relation.
what we were discussing yesterday was the mutual key. Do you want to?
It's also the partial key. The partial key and try to key will work together.
Oh, you want to do that?
No, we didn't.
We use relationship.
We are talking about something that is another person. I don't know what's your thing, but let's say it's.
Yeah, so B1 is the original one.
It's the one that. We want the person to have the rider of
Yeah.
They say, are you talking about this? Isn't the rider must be.
Ours is just like that.
Yeah. So our.
That's the certain one.
We saw it yesterday.
Yeah,
I was asking.
it's your award. Thanks you.
Yeah. One hesitation.
First relationship.
Why is this triangle? This
Yeah, this one is a relation. So we see integration. You have to have a rider and you have to have something else in order for the essay to actually, but the essay itself will be an empty state.
Would it be the same as that? It's radiation. Oh,
It's the same
thing.
thing. Yeah, it's still a relation.
Even though the question did say like.
That we must be that proceed.
But we just.
You want to change it? Then you can draw a square.
The problem is
Right.
So square.
Yeah.
What is that?
You will draw.
I wouldn't.
Yeah, I would be the
I was scared actual thing I
But
like.
we can change.
Yeah,
If it's zero.
we did ask. Yeah, he said he will talk party about it. Then I asked him very specifically, so is that a benchmark? How you all grade the thing? I just asked straight up.
Who is it?
They said as long as you all can justify that,
I would say
Justifications.
No, she doesn't like that. Just the notes.
your justification in the final report, then everything nothing else.
you first be that yeah, that we cover and ensure that we don't provide the limitation on the last slide. We have rule 1 to 3 and then exception. So just make sure that we deal with that.
你比他这里有开一点像。
The content will exist.
Oh no. The next set.
Okay. Have last. Think whether the team will be But your team is it is
Is it around 5,000?
I think but then that team might number right.
Riser fee, riser fee.
It's just a minute.
Yeah, it was same time. Just
Then you want to say that in the way.
Alright, let's come back.
We want to do, like, we really want to do
Okay, again, let me try to summarize, everything we did. Okay, again, the high level idea using the picture. So we started with some kind of primal problem, which has an optimal value. Okay, Z. We want to solve this problem. Now think about what we did in the simplex, algorithm lecture. There, the way we attack the problem, you can visualize it, is actually we are attacking the problem from above, right? If you think about our algorithm, the step one, maybe we are finding, say, an initial basic feasible solution somewhere here that probably has a kind of high cost, right? That's the initial solution. What can you expect? And then through the simplex iteration, we are basically improving based on this solution, right? Starting from this solution, we try to find the neighbors. We move to a solution with a lower cost. Okay, that's our next solution. We iterate it again. Next solution, and then at the end of the day, we may reach this Z value, which is the minimum cost. So that's what we call the kind of primal way of thinking about the problem. Attacking the problem from the above. The dual kind of idea is the opposite. Think about it. We're not thinking, in solving the original. We're thinking about finding a lower bound to the original bound. So you pick a Lagrangian multiplier. What we just did is basically picking a multiplier of 0. Right? That's basically throwing away the constraint. That probably gives you some lower bound. Maybe here. This is a lower bound to the unknown Z value. And then what we discussed just now is, can we basically pick a different penalty so that we can find a better lower bound? So we are attacking the problem from below. Okay? By picking another P, we're finding a better lower bound, okay, moving upward, and then picking another P here, and picking another P here, and so on. Okay. At some point, we did our best. Okay, we found the best possible lower bound. We can no longer improve it anymore. That's the W I just mentioned. Now, of course, I just said whether there's a gap here or not. That's the so-called strong duality. This is also known as the duality gap. Okay, so if strong duality holds, then there's no duality gap. Okay, if you work your best from below, that's the same as working from above. But for some of the non-convex problem, the duality gap is not 0. So in that case, the two problems are fundamentally different in some way. There's a gap between the two problems. But if the duality gap is 0, that's kind of like a perfect image, right? It's basically two sides of the same coin. You can interpret the problem in this way. The primal and dual problem are actually two sides of the same coin. All right, so that's basically the visualization of this one. Now, my second remark here is on the usage of this duality theory. Right? If you still remember, one kind of issue I mentioned in the first lecture is, for some of the problem, if it is, say, if the dimension of the problem is very high, or maybe later on we will talk about some of the integer programming problem. It's by itself it's already super hard. Okay, in those problems, it's not reasonable to expect you can always find the optimal solution. You can throw, say, a really large linear programming problem to the solver. It probably will take a lot of time to solve. Okay, I think the Groovy itself has a kind of a time limit function, right? Say 1 hour is the maximum you can tolerate, you can set the time limit to 1 hour. And then the group will stop at time 1 hour and will give you back some solution. Okay. Now the problem is the solution is not optimal. Then what do? Right, the question I raised in the first lecture is you should try to evaluate how good the solution is, right? But what's the benchmark you use to evaluate? Usually it's basically the optimal solution. Right? You want to know how far the solution I have right now is away from the optimal solution. Okay, let me try to visualize this. But suppose you have let the computer run for an hour and then let it stop. Say probably it stopped at the solution somewhere. Of course, you have no idea whether this is optimal or how far away it is from the optimal solution. So what you want to know, right, in evaluating the solution is this guy. It's the distance here. Am I right? The distance here, right? This is basically the optimal value of the best possible solution. This is the solution you get by solving for just an hour. Okay? The distance basically measures how you are away from the best possible. But do you know about this guy? No. You will only know about this guy if you can solve the problem, if you can get the z value. But if I can get the z value, what's the point of evaluating anyway, right? I already got the optimal solution. So this is again the paradox that I talked about earlier, right? I don't know about this guy, then how can I possibly evaluate it? With duality theory, you can do that. I will never get an exact number for this guy, but I can get an estimate of it once we have the duality theory. Because I can try to pick a Lagrange multiplier. For example, I pick a Lagrange multiplier here, which gives me a lower bound here. Again, you may not need to work the best possible. You don't have to solve the dual problem exactly. Okay, again, you don't have to find the best possible multiplier. You can pick some multiplier that gives you a lower bound here. Then the distance of this guy, you know. This guy is something you know. And from the picture, you already see that. The distance between your solution from the true optimal one is always bounded by this distance. Okay? So this is the estimate you can have for how good your solution is. Suppose, for example, if my solution in the lower bound here already has say is less than 10%, then you definitely know that you are 10% away from the best possible solution. It has to be better than that. If you're happy with this number, then you can stop with just 1 hour. Maybe that's fine. I'm okay with 10% of gap. Are we all clear? Okay. This is basically a kind of an important aspect of this duality theory. It can help you evaluate how far you are away from the best possible. In fact, this is already built in, in a lot of this, as part of the algorithm in a lot of these solvers. Okay, no solver, I think, is attacking the linear programming problem purely from the prime. Okay, usually they have a hybrid of algorithms that's simultaneously solving the primal and solving the dual. Okay, then at every instance, I'm basically kind of improving. At every instance, I have an estimate of the gap. Okay, how far away I am actually from being optimal. So that's basically a kind of use case for duality. Yeah. Now, this is okay. Then we can go back to this note now. So that's something we have already talked about. Again, one thing I want to repeat here is the sign of the penalty really relates to which side of constraint violation you want to penalize. Okay, this is important as we will see in a minute. If the constraint becomes inequality constraints, this will affect the sign of the penalty you want to choose. Okay, here we want to be able to choose both positive penalty and negative penalty. Exactly, we want to have the ability, because we want to have the ability to penalize both sides of violation. Okay, so this will become different once you have inequality constraints. Right, so that's the Lagrange step, and then the this due formulation of the due problem. Okay. Yeah, and that's the picture I just drew. Primal problem is attacking from above, the due problem is actually attacking from below. Okay, good. Yeah. Now I will just repeat the same exercise for linear programming problem. Okay. As long as you get all the idea, I think this is basically all the idea for duality theory. It's already contained in this simple example. Okay. Linear programming is just applying this idea to more complicated problems. Right. Linear programming problem. Let me write it out here. Again, I will just try to first do the derive this due problem for standard form. Okay. Standard form. For standard form problem, we have this minimize C transpose X. I have A1 transpose X equals to B1, and A2 transpose X equals to B2. AM transpose X equals to BM. And then we have this X non-negative, right? All the decision variables must be non-negative. Right. Exactly the same thinking. Right. The equality constraints here are giving us quite a bit of a headache before, right? We actually spent 2 weeks in trying to analyze what these constraints gives us. Okay. Now let's try to throw them away. Again, we don't just directly throwing them away, right? We want to make them soft. So in this case, I have M constraint. So I want to be able to penalize the constraint violation for each of the constraints in a separate fashion. So I want to assign a different penalty for different constraints. The first constraint, I assign a penalty of P1. The second constraint, I assign a penalty of P2, and so on. The last constraint, I assign a penalty of Pn. Okay. So this forms a vector itself. Okay. I'm calling this vector of penalty, I'm calling it P. I'm repeatedly using the same notation, but now P here now becomes a vector. Good. Then let's do the Lagrangian. Okay. Lagrangian relaxation. Oh, by the way, I'm only relaxing the equality constraints. Okay. If you want to do for the inequality constraint, you can actually do that, but it's completely unnecessary because these sign constraints are very easy to deal with. Okay, so that's why usually we don't try to relax the sign constraints. We only relax the hard constraints. Okay, so the Lagrangian relaxation problem now becomes, I have X, no, my decision variable is non-negative, so I don't relax this one. I have my original objective plus all the penalty terms. Okay, I'm summing up the penalty. I from 1 to n, then I have pi. That's the penalty for the ice constraints, and then times the constraint violation. Okay, the degree of constraint violation. Good. So this is the Lagrangian. And then you can still denote the optimal value to this problem as P. Now the G function is actually a multi-dimensional function because P is the vector now. So again, supposedly this problem should be easy to solve. This is still a linear programming problem. It should be super easy to solve. But of course, right now, with all the mathematical notation, it's a bit harder to see what the solution should look like. So we have to do a bit of a cleanup. Let me just do that here. So this is our Lagrangian. Okay, let me try to unpack things a bit. My first term, if I unpack it, that's going to be 3j times xj, living in dimension. And then the second term, let me just put x in front. Okay, I didn't do anything, just reorganizing this terms a bit. Now where are we going? Basically, I want to kind of group the coefficient together, right? All the xj, I want to group them together. That's where I'm going. Okay, and this term has nothing to do with x, right? It's just some constant. Once you give me a penalty, this is a constant. It has nothing to do with the optimization problem here. Of course, we can write this more compactly as P transpose B. It's just the multiplication of these factors. Now, for this one, if I want to combine the coefficients, of course, one way you can do is just you try to expand this. Right? This is just ay1 times x1 plus ay2 times x2 and so on. Okay, you expand everything, you group them together. Okay, but that's a kind of a more lengthy way of doing the math here. But if you're familiar with, again, the matrix notation, you have a shortcut, okay, of grouping everything together. Let me just do the shortcut here. Right? This stuff, you can actually write it as, again, more compactly as P transpose AX. Right? Because this is nothing but I'm first doing this row representation and then representing this AX as a vector of A1 transpose X, A2 transpose X, and then I'm using P times this vector. Now, instead of first multiplying A to X, I can first multiply P to A. This is where I can use the column representation of A. Okay, that's basically P transpose A1, A2, that's our column. AN X, right? And P multiplying this is the same as P multiplying each column. So this equals to P multiplying column 1, P multiplying column 2, all the way to P multiplying column n times we're okay. And then you do the vector multiplication.
And right is A and I is 1 to n.
That's the rows. The rows are from 1 to n. The columns are from 1 to n. Okay? Right, this is the column representation. This one is the row representation. This is I is from 1 to n. This is actually j. If I really need to recruit, you use the index. I always use j to denote the columns. Okay. And then this one you can now multiply. Okay, so this becomes summation j from 1 to n P transpose AJ times xj. Yeah. Then I can group this guy with the coefficient in front. Okay, then everything becomes a nice form. So let me just summarize everything here. So GP equals to minimization of x greater. Oh, sorry, I can put the constant in front. Okay, so the constant has nothing to do with the. So this constant, I put it in front. P transpose B plus the minimization problem here. X non-negative, and then summation j from 1 to n, Cj minus P transpose Aj Xj. So that's the, after, just some algebra steps, if I clean up the objective function, this is the optimization problem we are trying to solve. This is the relaxed problem. Almost no constraint, except the non-activity. This supposedly should be easy to solve. What's the solution? Now, don't be fooled by the complicated expression there. This is just constants, some coefficient. Let me just give you an example. Okay, you simplify things a bit. All right. Think about the following. This is a special case of this one, right? With n equals to 2 and the penalty 0. Right? Essentially, I'm throwing away the constraint. And for two-dimensional problem, if I throw away all the equality constraint, I get this. What's the solution to this one? 0. What if C1 is negative? Minus infinity, right? If C1 is negative, what do you want to do? You want to let this x1 to go all the way to positive infinity. In this case, you get negative infinity. It doesn't matter what C2 is. Okay, you always get negative infinity. If C2 is negative, the same. Only when C1, C2 are now negative, yes, x1, x2, 0. That's the best you can do, right? Do nothing, you get 0 cost. If they are cost. If they are not cost, the revenue, right? Then you want to do produce, right? So that's basically what happens. Super easy. Then the above one is the same. Okay, the above one is the same. So this one, okay, let me just write it down below. It's going to be P transpose B plus. Essentially, we have two cases. The minimum value of the above problem is 0 if all the coefficients in front of the x are non-negative. This is the case where it's just 0. Otherwise, it's negative infinity. Are we okay? So basically, we know about the value of GP2, right? It's either P transpose B if this condition holds, or it's going to be negative infinity otherwise. So now, what we have accomplished so far is basically if as long as you give me a vector of Lagrangian multipliers, I can easily solve this relaxed linear programming problem by hand. Now again, let's get back to the original purpose of doing the Lagrangian relaxation, right? We do Lagrangian relaxation because we want to choose a Lagrangian multiplier penalty smartly so that we can get a good lower bound. Okay, so then we need to find out how do we find the right Lagrange multiplier. That's the dual problem. Okay, that's the dual problem. Well, let's think about this question here. If I just look at the expression, if I don't choose my Lagrange multiplier carefully, if I end up making some of the coefficient to be negative, I will get negative infinity. Is this a good lower bound? Completely useless. Anything has negative infinity as the lower, completely useless. So when I'm choosing the Lagrange multiplier, I have to be careful so that I don't fall into this region. In other words, I want to guarantee that my Lagrange multiplier satisfies all this inequality. This becomes a constraint when I'm choosing the Lagrange multiplier. Are we okay? And once my Lagrange multiplier satisfies the constraint, what's the lower bound I will get? P transpose P. And I want to make this maximum. I want to maximize this guy. So that gives us this dual problem, right? This dual problem in this particular case becomes maximize P transpose B. That's our objective, subject to. Again, let me try to reorganize this constraint a bit so that I can move, I can move the decision to the left-hand side and then the constant to the right-hand side. That's basically our constraint. So that's the dual problem to our original primal problem. Okay, what kind of problem this is? Yeah, this is linear or not? This problem. Linear. Don't be fooled by the new notation, okay? Now I'm calling the decision variable P instead of X, but this is still a linear function. Okay, instead of C transpose X, I'm writing vector multiplication by putting the decision variable in front. P transpose P, they're the same stuff. And constraint are all the same, right? So this is, again, a linear program. So now you see, so this kind of whole duality theory, there's a new perspective, but there's no free lunch. Okay, you cannot expect, okay, I start with a primal problem, I do all the steps, then the dual problem suddenly is something super easy to solve. This best Lagrange multiplier, I can somehow magically find it somewhere. No, there's no free lunch. If you want to find a Lagrange multiplier, the best Lagrange multiplier, you still need to solve another linear programming problem. So that's the dual problem here. But of course, there could be cheaper lunch. Okay, sometimes the dual problem could be easier to solve than the primal problem, or vice versa, depending on the problem structure. Very good. So that's basically the duality theory. If I specialize it to linear programming problem, you start from a linear programming problem, the dual problem becomes another linear programming problem. So that's the mirror image here. Okay. This one, I mean, notation-wise, you can also write it in a more compact format. Okay, sometimes we just write it in this way. Okay. This is a slightly different from the usual convention, right? When we are writing the primal problem, we're organizing the constraint in a column fashion, right? But if you are writing in this way, this is what? This is actually a row vector. So in this case, I'm basically writing the constraint in a kind of horizontal fashion. Something. This is a row vector less than equal to another row vector. Okay, but this is no real difference. Okay, you can do the transpose on both sides, then you get back this column and then a representation. Quite compact. Okay. So again, going back to my earlier points, you see that if I start from a standard form problem with all the equality constraints, I don't have any, sign constraint on the value of p. Okay. So I'm free to choose this p to be either positive or negative. Things will change if I deviate from the standard form problem. For example, let's think about this one. Then what happens if my primal problem is something like this? Instead of I have equality constraints, now I have greater than equal to type of constraint. What will the do problem look like? Of course, you can just repeat all the Lagrangian steps we just did. Okay, it's going to be all the same, but you don't have to do all the steps. Okay, there's a smarter way of doing this. You can just first transform this to a standard form problem. Just apply the formula we just got. Okay, so this is where I will be doing. Right. Now this should be very familiar to you guys. So the standard form for this one is going to be C transpose, 0 transpose, and then I have X, and the slack variable S, and then the matrix is what? The matrix is going to be A. Now we're subtracting the slack variables, right? So I will have a negative identity matrix equals to B, and then we have X, S, with equal to 0. Now, as long as you know how to write down the dual for the standard form problem, then you know this one, right? So you just need to replace the A matrix here by this new one, and the C vector by this new vector. That's it. Okay. The dual problem, I'm just copying the formula. That's it. Okay. The dual is going to be maximized. The B vector doesn't change, right? It's going to be the same as before. So I still have P transpose B subject to no, it's P transpose the new matrix A negative identity matrix less than equal to C transpose 0 transpose. That's it. That's it. Okay. Then you can just clean up the constraint a bit, right? This is just P transpose A less than equal to C transpose, and P transpose the identity matrix minus identity matrix less than equal to 0. And P transpose the identity matrix is just P itself. So we will have maximize P transpose B subject to less than equal to P transpose and oops, P non-negative. So that will be the form of the dual problem if I start from this greater than equal to type of constraints. Now you will see that once I have inequality constraint, correspondingly there will be a sign constraint on the Lagrangian multiplier. Let's think about why that's the case. Intuition, okay? Again, you can think about the kind of a penalty we are adding here, right? The penalty, let me try to write out one of the constraints. I have too many constraints here. I will just use one of the constraints as an example. Right, for example, here, let's say a representative constraint is AI transpose X greater than equal to BI. Okay. If I associate with a penalty to this guy, right, which is PI, and move it to the objective, then I will get the penalty of this form, right? Yes, that's going to be the penalty I have. Now, unlike equality constraints, here I can only have one side of constraint violation. If I look at the sign of this guy, bi minus ai transpose x, okay? If the sign of this guy is less than 0, I'm actually happy because the solution in this case is feasible in my original problem. If the sign of this guy is positive, then this is bad. Right? If you have positive value here, there is constraint violation. Are we okay? So this is different from the equality constraint. Now then think about how should I choose my penalty. Again, you don't want to penalize constraint satisfaction. You don't want to penalize constraint satisfaction. Ideally, you only want to penalize constraint violation. Right? This is the case of constraint satisfaction. If I choose pi to be negative, what am I doing? I'm adding cost. Right? You satisfy your constraint, but actually I'm charging you money. Okay. So that's why in this case pi has to be non-negative. Are we okay? So the sign of pi has this relationship with the kind of a type of constraints you have. Any questions about this so far? Okay, then I think we can get back to the slides here. We have all the steps written down. Yeah, that's basically the last comment I made, right? In the original problem, when we write down the due problem, there's no constraint on P because I have the freedom of choosing the positive P and negative P to penalize both sides of violation. But if you start from a non-standard form problem, for example, this greater than or equal to type of constraints, when you write down the due, there's a natural kind of sign constraint that's going to be pop up. You can imagine, right? If you start from less than or equal to type of constraints, then the corresponding penalty will also become negative in this case. Yeah, that's basically the rationale I just mentioned. All right, finally, this is just for your reference, okay? If I give you any kind of a form of linear programming problem, so this table basically helps you to avoid the steps I did in the class. You don't have to basically go to the Lagrangian relaxation and then solve the relaxed problem and then derive the due problem. There's a kind of a table-like solution for you here. Okay? You just need to kind of need to learn how to read the table. That's it. Okay, then if you are given any linear programming problem, you can easily write down the due problem. So let me just explain this a bit. Suppose say we are looking at a primal problem on the left. Then the problem on the right basically gives you the form for the due problem. Okay. Again, for every inequality constraint you see, it corresponds to some Lagrangian multiplier. And as I just said, the type of inequality constraints will affect the sign of the due variable or this penalty. If it is equality constraints, no sign. If it is greater than or equal to type, the multiplier has to be non-negative. If it is less than or equal to type, the multiplier has to be non-positive. Okay. Now, it turns out that the type of constraint you write, right? So just now we are basically worked on the case where x is all non-negative. If x is all non-negative, then you get this less than equal to type of constraints in your due problem. But what happens if some of the variable is not positive? Then the sign is flipped too. Okay? If some of the primal variable is unconstrained, then you will end up with an equality constraint, okay, in the due formulation. So that's basically summarizes all the possible variations you can have. But you also see a pattern here, right? There's some relationship between the primal constraint and the sign of the dual. There seems to be also some relationship between the sign of the primal and the constraint of the dual. So in fact, if you take the dual to this problem again, you get back to this one. So that's why they are duality, right? So they are basically mirror image to each other. Okay, the primal is the dual. So the primal is the dual of the dual problem. Okay, the other way also around. So are we good? So you can also interpret this x variable as some kind of a Lagrangian multiplier for the constraint down below here. That's why they are mirror image to each other. So that's the kind of a table that you can utilize to write down the due problem. So later on, you will have some homeworks that you can use this table. So, by the way, it works in both ways. If I give you a primal problem that's a maximization problem, then you can also use the table to get the due out of that. All right, let me just finally wrap up with this summary of this duality theorem. Okay, the first point I just mentioned, the dual of the dual is the primal. Okay, so the two problems are dual problem to each other. And the second point is something that we also already mentioned, the so-called weak duality relationship. In other words, any due solution, okay, if you evaluate the value at the particular due solution, it provides a lower bound to the problem. Okay. Conversely, any solution to the primal can also give you an upper bound to the due problem. So that's basically the inequality here. So using this inequality, you can then infer a couple of things. For example, if the primal problem is, say, unbounded, by convention, usually I will refer to the minimization problem of the batch as the primal. Okay? If this primal problem is unbounded, has negative, say, infinity velocity, what do we know about the dual? The dual has to be infeasible. Again, because if the dual has some solution, it naturally provides a lower bound to your primal, but then the primal problem cannot be unbounded. Okay, conversely, if the primal problem is unbounded, then the dual has to be infeasible. And similarly, if the dual problem is positive infinity, then the primal problem has to be infinity. The last point I think is the most useful one. The duality theory actually gives you a different kind of optimality condition. If you have a certificate without checking all the other solutions out there. Okay, it basically says the following. Suppose you can guess a solution to the primal problem. And then you also guess a Lagrangian multiplier. If the cost under your proposed solution and the value under the lower bound, okay, under your proposed Lagrangian multiplier matches, then both of them are optimal. Right? If you can find two solutions that closes the gap, right? Remember the picture, then of course, by definition, by this weak duality, both of them has to be optimal. This is sometimes can be useful, especially for some of the hard problems that we don't know how to solve. But you know structures, then you can guess. Okay. This gives you a kind of a proof or certificate that your guess solution is in fact optimal. But what this doesn't tell you is the kind of existing question. Can you always find these pairs that closes the gap? So that's the question answered by the strong duality result. The strong duality tells you yes. Okay. For linear programming problem, you can, as long as the problem has a solution, okay, it's not unbounded or infeasible, then you can always find a pair of solutions that closes the gap. Okay, so that's strong duality. Are we okay? If the primal has a solution, then the dual must have a solution. And the optimal value of the two problems has to be equal. So the table here is just a summary of all the cases we discussed. Just provide the summary. For example, if I interpret this the rows here as what can happen to the primal problem, we can only have three cases, right? Either the primal problem has some finite optimal solution, or the problem is unbounded, or the problem is just infeasible. If the primal problem has a finite optimal solution, the strong duality tells you what? The dual problem has to have a finite optimal solution. It cannot be unbounded, it cannot be infeasible. If the primal problem is unbounded, this is weak duality. The weak duality tells you the dual problem has to be infeasible. This is the only possible case. The other two cases are impossible. Okay. So the only scenario that's not exactly implied by these two strong or no weak duality is the last case. Okay. If the primal problem is infeasible, of course you know that the dual problem cannot have a finite optimal solution, right? Because otherwise, okay, if the dual problem has finite optimum by strong duality, the primal also must have. Okay, so the primal problem cannot be infeasible. So if the primal problem is infeasible, then these are the only two possible cases. The dual problem could be unbounded, the dual problem could be infeasible too. So you could have a case where both the primal and dual are infeasible at the same time. But that's basically a kind of a summary of what can happen to this primal and dual problem. Are we good? Any questions about this stuff? Okay, yeah.
So you said weak duality just means that the dual solution is lower bound of the primal solution, and the primal solution also serves as an upper bound for the dual solution, right?
Yeah.
So does that mean that the point dual of the dual is primal only applies to problems that have strong duality?
Very good question. I think so.
I actually don't understand what exactly non-convex problems without strong duality are. The initial question I want to ask is, if I take the dual of the dual
Yeah.
for a problem without strong duality,
Yeah.
would it still turn out to be the primal?
I don't think that's guaranteed if you don't have strong duality. I don't think that's guaranteed. I've never looked into this question, but this is based on my hunch. I don't really exactly know for sure the answer. If you don't have strong duality, my intuition is that you don't always get back, because fundamentally I think the two problems have a gap. They are no longer mirror image to each other. So that's why I say if you take the dual to the dual problem again, you may not get back to the primal problem. But this is not the case when the duality gap is 0. Okay. So they are kind of the two sides of the same coin. That's the nice case. Okay. Again, I mean the non-convex problem, right? As I said, is difficult. You can view the difficulty from a lot of perspectives. Local solution doesn't imply political solution. Strong duality fails. I can only attack the problem from one angle. But I mean the weak duality still holds. So in some sense, even if the problem is non-convex, I still have, in some sense, a method of doing this. This picture. This picture holds regardless of the problem is convex or not. But even if there's a gap here, I can still do this. But one possibility here is that suppose the gap is super huge. This one, 30%. Then you have for non-convex problem, then you don't know whether the gap is huge, is because you are not doing your best, or it's because the problem is fundamentally difficult. the 30% is fundamentally the gap of the problem, not because you are not doing your best. But for problem with strong duality, as long as there's a gap, it means that you are not doing your best. You can do better. Okay? That's something you do know. But for non-convex problem, that's an issue that's left open. Okay? Any other question? Okay, good. So that's the kind of a more theory part. Next week, we are basically going to kind of repeat the same stuff, but then we will work on the specific example of this production. Okay, there you will see that all the stuff we have, in fact, also have an economic interpretation behind. Okay, what this Lagrange multiplier implies. Okay, we were just using a different language of doing the same stuff. Okay? Instead of the lower bound and stuff, you will see that the Lagrange multiplier corresponds to some kind of shadow price of the constraints you have, and based on that, you can do some sensitivity analysis. Okay, so that's what we will do next week, and I will stop here. See you guys.